Welcome to this video on circular orbit ratios. This video I'll be looking at a number of mathematical ratio questions relating to two satellites around the planet Earth. So first of all, let's look at the equations we have available when we look at the forces between a satellite and Earth. So first of all, we've got Newton's law of gravitation, which we've all seen before. It involves the mass of the two objects, big M being the mass of the Earth, little m being the mass of the satellite, and r being the separation radius from the center of both bodies. We've also got the fact that a satellite moves in a nice circular path around the Earth, so we consider that force also to be circular motion. So we can also use F equals mv squared on r, the traditional circular motion equation. There's a second variation of the circular motion equation. If we consider a circular path, for example, this inner satellite goes around in a circular path, we know it covers a circumference of 2 pi r in a time of one revolution period, t. So we can replace v with the equation v for the speed is equal to 2 pi r over t. 2 pi r gives you the circumference, the distance traveled, divided by the time taken for one revolution, which is period. When I sub that in and square it, this is the end result. So it's really the same equation, just using radius and period instead of velocity. And finally, the traditional weight equation that we're used to, whereby an object's weight is a product of its mass and the gravitational field strength. So there's our traditional equations. Now recall, please, that F equals ma, so we can rearrange that to find a, the acceleration, is equal to the force, the net force, divided by the mass. Okay. So if I were to take those previous 4 or 5 equations and divide the force equation by the mass, and effectively divide by a mass, divide by a mass, divide by a mass, I can rewrite those equations as acceleration equations. So here we have now the acceleration of a satellite. It can be calculated by the product of the universal constant times the mass of the Earth divided by its radius squared, or it can be found, the acceleration of the satellite, by taking its speed, squaring it, and dividing it by the radius, or we can multiply its radius by 4 pi squared and divide that by the time it takes one revolution squared, its period, or we can work out its gravitational field strength. They're all different ways of finding the acceleration of a satellite around a planet. So my question for today, the scenario, I have two satellites, satellite 1 and satellite 2, as seen on our screens. They're in circular orbits around the Earth. Their orbital radii are r, the shorter one, and 2r respectively. So we don't know the actual numerical values, but we know that the second satellite is double the radius of that of the first. And the mass of S1 is twice that of S2. So the mass of this satellite is twice the size of satellite 2. The task for today's video is to calculate the value of the following ratios. I want to work out what is the ratio of the orbital speed of satellite 1 compared to the orbital speed of satellite 2. That's the first task. The second task, calculate the orbital period of satellite 1 as a ratio to that of satellite 2. And the third and final task is calculate the ratio of the acceleration of satellite 1 to that of satellite 2. So this is a little bit more mathematical than normal, but let's give it a go and see how we go. So first of all, we want to look at finding out the ratio, the orbital speed of satellite 1 to satellite 2. So I've got two satellites. Both of them have got the constant values of the mass of the Earth are relevant to both of them, and the universal constant g. Their radiuses change and their masses change, and we're trying to work out the ratio of v1 to v2. So let's look at these equations we have up here for the acceleration that we derived earlier. We can see the equations that are relevant to this particular question, they have to have the v in it, because we're looking for a v1 and v2, so this part of the equation has to be used. And we know g and m, and the r, we have r ratios as well. So these are the two equations we're going to use to try and solve this ratio problem. We're given nothing about acceleration, nor are we given anything about the period or the gravitational field strength. So we have to use these two equations to try and solve this problem. So here we have the two equations we're going to use to try and find the ratio of the velocity of 1 compared to the velocity of 2, or the speed rather. So first of all, let's identify what's constant for both satellites. So in this equation, we see that both, no matter if you're satellite 1 or 2, universal constant is always going to be constant. That's why it's called the universal constant. And the planet of the mass is constant. What I want to try and do now is rearrange my variables to get all my constants on one side and my variables on the other. So I'm going to leave the GM as a constant on the left-hand side, and to do that I must multiply my r squared across to the right-hand side. Okay, now I've got constants on the left and variables. So in both satellites cases, the product of GMN will be the same. Okay, and of course I can make that simpler by dividing the r, when I divided that across, my r squared divided by r just leaves me with GM equals v squared r. Okay, so now I've got all my constants on the left-hand side, all my variables on the right-hand side. So, satellite 1 and satellite 2 both have the same left-hand side, which means the right-hand side must be the same for both satellites as well. So I can now look at the right-hand side and say, well, the velocity of 1 squared times its radius will be equal to the velocity of satellite 2 squared times its radius. We've now came up with a new expression that we can use to hopefully find our answer. So v1 over v2, speed 1 over speed 2. So here's our equation we started with. I'm trying to get v1 divided by v2, so I'm going to divide my v2 squared over to the left-hand side. And finally, I'm going to divide my r1 over to the right-hand side. I've now got an expression with just v1 and v2 on one side of my equals and other variables in terms of r on the right-hand side. I can further simplify that. v1 squared over v2 squared is v1 over v2 all squared is equal to r2 over r1. And to get v1 over v2, which is our final answer, I want to now take the square root of both sides. So finally I've derived an expression of the speed of satellite 1 divided by the speed of satellite 2 in terms of values we know, r2 and r1. I'm now going to use that relationship to sub in our values from the start of this problem. So we knew that the second radius was double that of the first radius. So I've said let the first radius be a value r, and the second radius is double that. Easily we can cancel out the two r's, and we have the ratio of speed of satellite 1 to speed of satellite 2 will be the square root of 2, or 1.4. A few mathematical steps, maybe go back, review and replay that one. Task number 2, we want to do the same thing, but this time we're looking at the orbital period of 1 to the orbital period of 2, the ratio of the two. Okay, so we want to know about T1 over T2. Okay, again, we have mass of the Earth common to both. We have universal constant common to both. We have information about the radius masses, but this time we want information about T1 and T2. So we've got to choose an equation that's got T in it, our period. So 4 pi squared r over T squared, we have to use this one. Okay, because we want to find information out about the T's, the period ratio. Okay, and again, we know G, we know M, we have information on R. So they're the two equations we're going to use because we don't know anything about the acceleration. We aren't given anything about the gravitational field strength. And velocity or the speed we don't know. This is a new situation. We're not going to use our previous information. So we're choosing these two equations. So GM over r squared equals 4 pi squared r on t squared is the equation we're going to use. Okay, let's identify the constants. For both satellite 1 and satellite 2, G and M are constant for both of them. And for example, we know G is a universal constant, and this mass of the Earth is what's attracting satellite 1 and satellite 2. It's a constant for both. 4 and pi squared are constants as well. So we want to rearrange our equations to get all our constants on one side of the equation and our variables on the other. So let's do this first. Okay, we're going to try and move our 4 pi squared over to the left-hand side. At the moment, it's multiplying the rest of this fraction, so let's divide it across. All done. All our constants are on one side and our variables are on the other side. All right, now again, for both satellites, given that GM 4 pi squared is constant for satellite 1 and satellite 2, that means the r cubed over t squared, the right-hand side, should be constant for these two as well. So we know that the radius cubed divided by the period squared for satellite 1 will be equal to the radius cubed divided by the satellite's period squared for satellite 2. Here's our expression. Now let's see if we can transpose this and get it in terms of T1 and T2. So we've got T1 on the bottom, that's not really much use. What we've done here is simply flipped our fractions. Okay, so T1 squared over R1 cubed, I've inverted to put T1 squared on the top. And on the right hand side, I've done the same as well. I've flipped my fractions T2 squared over R2 cubed. That mathematically is correct. Okay. Now let's see if we can simplify. I want T1 over T2 eventually on my left-hand side of this equation. I've got T1 squared Here's T2 squared. Let's divide that across the left-hand side. Very good. And at the same time, I'm going to multiply my R1 cubed across to the right-hand side. Looking close to our final. We wanted T1 over T2. At the moment, we've got T1 squared over T2 squared. I can express that as an all squared. Okay. I can take that and say T1 squared over T2 squared is the same as T1 over T2 all squared. And again, instead of saying R1 cubed over R2 cubed, I can say it's R1 over R2 all cubed. So getting T1 and T2 by itself as a fraction, I simply have to take the square root of the right-hand side. Square rooting this, we'll get rid of the squared. Square rooting this side will give me the square root of R1 over R2 all cubed. Now, it's a bit more complex, but now we can sub in our values. Radius 1 was a value of R. Radius 2 was 2R. Again, we can divide through the top and the bottom, the numerator and denominator, by R, and that leaves me with T1 over T2, the period ratio of the two satellites, is equal to the square root of a half to the power of 3, or 1 cubed is 1, 2 cubed is 8. The square root of 1/8 is 0.35. Again, a few mathematical steps, but it's a good way to work out ratios. Our final question was to work out the ratio of the acceleration of satellite 1 to that of satellite 2. All right, this time again, we've got our equations. We need to find acceleration, so we have to use this equation. And again, we have the g and the m and the r, so we'll use these two equations. We don't know anything about the velocity, we're not using the period, and we don't know the gravitational field strength. So let's give this a go. Again, all I want to do in the next step is move all my variables, identify my variables, and identify my constants. There's my constants. I need to get these on one side and the variables on the other. Let's have a look. So we've got a equals gm over r squared. Looks like I've shortcut this one. So I've multiplied my r squared across the left-hand side, and that leaves me with r squared equals gm. Then I've just rewritten it with the known constants on the left-hand side and the variables on the right-hand side. So once again, for each of these satellites, the product of g times m is constant, which means the product of a times r squared will be constant. So the acceleration of satellite 1 multiplied by its radius squared will be equal to the acceleration of satellite 2 by its radius squared. Here's our equation we just derived. We want to rearrange this so we can get a1 divided by a2. Well, that would be easy. I just need to divide a2 across to the left-hand side. And now I need to divide r1 squared across to the right-hand side. I've now got the expression I was after. It'll allow us to do our calculation. All right, so let's have a look. This can be written as a1, the acceleration of satellite 1, over a2, the acceleration of satellite 2, is equal, instead of saying r2 squared over r1 squared, we can say it's r2 over r1 all squared. This makes it a bit easier. So we've got our equation. We now need to sub in our variables that we know. So we knew that radius 2 was 2r and radius 1 was r. It's twice the size. We can divide through by the r's, and we see that this bracket now becomes a 2. So the ratio of acceleration 1 of satellite 1 divided by the acceleration of satellite 2 is equal to 4. That's our third and final answer. Look, I hope this has helped you understand the concepts of ratios of satellites around a planet. This can also be used for ratios of, say, planets around the sun. Anything that's got a large central mass and an orbiting satellite or planet can use these ratios. As always, if you enjoyed this and got some benefit, I'd ask you please to like, to share, and to comment on this video, and appreciate it if you'd subscribe. Thanks for watching.